Let's just get some notation out of the way with differential calculus. Suppose we have got a function x cubed. We know what that looks like. It's got a point of inflection at the origin. I'm going to tell you that the derivative of this function is 3x squared. So we write that as f prime of x being equal to 3x squared. Equivalently, I could also write that d dx of x cubed is equal to 3x squared, where the notation here is implying that the derivative is a small change in x, which is what d dx means. And they're both telling me the same thing, which is the gradient function or the derivative function. So in other words, we can use this notation interchangeably, which is that f prime of x is equal to d dx of f of x. And just to consolidate this understanding of a differential calculus, we can see that f prime of x being 3x squared is going to tell us everything about the gradient of the original function, which was x cubed. We can take the point when x is 1, for example, we can see the corresponding y value is 3 on the gradient function, or our derivative. This implies that the slope at that particular x point is going to be 3. And this works for any x point, as we can see. So we're going to be looking at differentiating using the power rule. Suppose we've got a function which is f of x being equal to x to the power of n. I would say that the derivative is n times by x to the power of n minus 1, where that n comes from the power. And if we have got a constant term, it has no derivative. So we might see a question like, differentiate f of x being equal to 2x squared. What we're going to do to calculate the derivative is use the power rule, where the 2 from the power is going to come down and multiply by that 2x squared, and we're going to take 1 from that power, giving us a resulting derivative function of 4x. Again, we can interpret this with 2x squared and its derivative function 4x. What this is going to tell us is that at any x point, the corresponding y value on the derivative function tells me the gradient on my original function. We can see that for the point, x being 1. We can also have a look at the point, x being equal to -1, where the corresponding slope on that quadratic is -4. And if you understand the relationship between these two functions, with a function and its derivative function, then really you understand the crux of differential calculus. So here we've got a function to differentiate, and all I'm going to do here is use my power rule, where I'm going to take each term at a time. So here my first term is 2x to the power of 4. What I'm going to do is I'm going to say it's 2 times by 4, x to the power of 4 minus 1, where that 4 came from the power. And I'm essentially going to do that for every single term here. And where our last constant term will just vanish because it has got no derivative. And we can clean this up a little bit. We can say we've got 8x to the power of 3, subtract x squared minus a half x, where this stuff here just cleaned up to be 1x squared, and this stuff here just cleaned up to be negative a half x to the power of 1. And so I would say that this is my derivative of the function. Suppose we've got a function that looks like this. Only trick is here is that we have got one of the terms which has the square root of x. No tricks here. I'm just going to rewrite the function. However, instead of expressing it as 2 square root of x, I know that when I square root something, that is taking to the half power. So I'm going to rewrite it like this so I can apply the power rule. I'm going to differentiate the function. I'm going to have 5 times 2 x to the power of 2 minus 1 plus 2 times by a half to the power of x, a half minus 1, and that 3 term vanishes. Cleaning this up a smidge, we've got 10x plus 2 times a half is just 1. X to the power of a half minus 1 is negative a half. Again, I can clean this up a little bit. I can say I've got 10x plus 1 on x to the power of a half. getting that negative index. I'm just cleaning up using index laws there, positive indice on the denominator, and I'm going to express it as a surd. This is my derivative function. So that's just a little bit of practice using the power rule. And let's see it with a little bit of context. So here we've got a curve given by 3x cubed minus 6x squared plus 1. The question is asking us to find the gradient of the tangent line to the curve at the point x being equal to 1, y being equal to -2. So that is a coordinate point on our curve, which is our cubic curve. Hopefully we can visualize that. Now, in order to calculate the gradient, I'm going to need to know the derivative, because the derivative function tells me everything about the gradient of the original guy. So I'm going to differentiate. Okay, where I get a derivative function, which is f prime of x, of 9x cubed minus 12x. Now remember, by the definition, this derivative tells me everything about the slope on the original curve. So I want to know, what is the slope? Or in other words, remember this is m. So what is m equal to, or what is f prime of x equal to, when x is equal to 1? Because that is the point given in the question. So I'm going to determine, what is f prime of 1? And I can see that it equals -3. I'm just going to wrap this up by writing my therefore statement. I would say, therefore, m equals -3 at the point x equals 1 on my original function f of x. And that is the interpretation of the derivative.